Hi everyone, and welcome for watching my talk. My name is Camila de Sá-Freitas. I am a PhD student at ESO, and today I'm going to present what I've been working lately. Stay tuned because everything I'm showing now will be submitted very soon. We're going to show today a new methodology on how to time the moment that bars formed in the universe. So why do we care about when bars formed? Basically, we want to understand how different galaxies' evolution processes are responsible for different cosmic epoch. So what we do know is that in high redshifts, you have a lot of turbulent dynamics, which are because of interactions and mergers, and these are responsible for driving how galaxies will evolve and change with time. But when we look at galaxies close to us in the local universe, what we have mostly is these galaxies with order dynamic and cold dynamics especially. So we want to understand what happened in the universe that in the beginning, you would have external processes as the main responsible for driving galaxy evolution. And now you have more internal processes. You have secular processes responsible for driving galaxy evolution. So we want to understand when you had that switch. And how can we do this? We can time when the bar formed in galaxies, especially because the bars are the main one responsible for secular evolution, that is the internal evolution in the galaxy. So how can we time when bars formed? We can use nuclear disks. But before explaining, I want to tell you what are nuclear disks. So here we have NGC 1433, is a very massive disk galaxy, and we can see in the very center of it where the square is a second disk, the nuclear disk. And basically we can understand properties of the galaxy studying this very central region. And now I'm telling you that we can even time when the bar formed. How can we identify the nuclear disk? So one way of doing this is using the kinematics. Here I'm showing you the velocity map and the dispersion map on the bottle. And it's pretty clear, especially in the dispersion map, that you have a drop in the center. So instead of the expected behavior of increasing dispersion, especially when you would have a classical bulge, you have a drop. This is because you have a second disk, the nuclear disk, that is in the very center of the galaxy. And if you look in the velocity, you can also see a different behavior. You can see an increase on the velocity rotation here. So these are nuclear disks. For a long time, they were called as pseudo bulges, but they are completely different things. So we're going to, from now on, only call them nuclear disks in this talk, okay? So how can we time bar formation using nuclear disks? What we have from a lot of simulations and theoretical studies is that the moment the bar form, you have tangential forces taking place, and this will make gas inflow to the center of the galaxy. So the bar, because of the bar, the gas outside will start going to the center part of the galaxy. And basically, you form the nuclear disk. And we know that this happened within a couple of million years, which in extragalactic time is basically at the same time. So if we can time the moment that the nuclear disk form, we also have the epoch that the bar forms. And more than this, we expect that the radius of the nuclear disk will be associated with the bar resonances. So the nuclear disks and the bar, they are connected, not on the moment that the nuclear disk form, but also how they evolve. They evolve together. So we expect that the smallest radius for nuclear disk would be around 40 parsecs for simulations. And what we think is that as the bar grows, you will have this bar resonance radii also growing inside out. So the place that the gas stops and forms stars will also change, and then you will build up the nuclear disk. This is what we call inside out growth. And we have some expected consequences from this growth. The first one would be that the outer part of the nuclear disk will be younger because they are recently formed. And we also expect that smaller nuclear disks will be associated to younger bars, basically because the bar will form small, and then the resonance will also be in very small radii, around 100 parsec or less. So how can we time the moment that the nuclear disk form? Because it's also not extremely straightforward. We have to keep in mind that the nuclear disk is sitting on top of the main underlying disk. and the main disk is old. So when we derive age radial profiles such as this one, here the dashed line indicates the radii of the nuclear disk. When we derive this kind of age, we have to keep in mind that this is the mean age of the total light we are observing, and the total light has informations of the old main disk and the young nuclear disk. So this light is tangled with both informations. So briefly, our methodology consists in creating representative spectra to recreate what we expect to be the underlying disk below the nuclear disk. Once we do this, and we have a lot of steps here that I'm not going into details, once we do this, we can create the underlying main disk and subtract from the original data. And doing this, we're going to have a difference, and the difference we expect to be the nuclear disk. And then we can derive stellar properties independently for the nuclear disk and the main disk. One example of how this looks like is like this. We have an illustration here. So we have the nuclear disk in the very center of the galaxy. We use a ring outside of the nuclear disk to derive that spectra that I said. So the excess, we have a lot of treatments, and then we derive the representative spectrum and we create the representative main disk. So we disentangle the main disk and the subtracted data cube that we expect to be the nuclear disk isolated. So this is how it looks like, more or less. We have 3 data cubes. We have the original one. We're using data from Muse. Muse is an incredible IFU. So we have 1 spectra for each spexel. And this is how the nuclear disk of NGC 1433 looks like on your left. And I'm just showing you the sum of the fluxes inside Muse. Just keep in mind, this is only the nuclear disk, okay? In the center, I have the main disk that we create with our methodology. And then in the right, you have the difference between these two. Okay, so it doesn't look a lot different, but when you start deriving the stellar properties, you see that it is indeed very different. So here's an example of the age map for the original data. Blue is young stars and red is old stars. And of course, you have the mean age for each spexel. In the center is the age for the main disk, so we can see that it is older than the original data. And then on the right, you have the difference. And we can see that it did got young, especially on the outer part of it, where the subtraction is more efficient. So with that methodology, how can we time the moment that the bar formed? We decided to use the star formation history of these components independently. So what do we expect? We expect that the star formation history for the original data to be something like this. So inside the nuclear disk, we expect to have an old star formation history that declines with time. And then you have a younger burst. This is the formation of the nuclear disk. So what we expect by disentangling the structures is that the main disk will map the old star formation and the nuclear disk will map the young star formation. So one way of timing the moment that the bar formed is taking the ratio between the nuclear disk and the underlying main disk. The moment that this ratio is above 1 for the first time is the moment that the bar formed. So this looks more or less like this. Just to keep in mind that here times evolve from right to left. Here we have the look back time. So this is the ratio, and in yellow, orange, you have the moment that the bar formed. Well, in an ideal world, this sounds efficient, but we wanted to make sure if this is a good criterion. So we did the same methodology for simulated galaxies. So we would have more control and understand the consequences of our methodology. So how does this look in simulated galaxies? This is one of the results for simulated galaxies. I have the same color code. So red is original, blue is subtracted, and green is representative. It's not as perfect, we can see, especially in the old star formation, for example, you still have something left in the subtracted. And this is, of course, because we're taking a ring outside. So the ring will not be as old as the main disk beneath the nuclear disk. But that's okay, because even with that, we can see that the ratio above 1 still can time the moment that the bar formed. So for this simulation, we have that the bar formed in this yellow moment, and the ratio above 1 is a little bit before that, but this is 300 million years. and still when extragalactic ages, it's inside an error. So we can say that the fraction above 1 for the first time is a good way of timing at least the epoch that the bar formed. We only have to keep in mind some cases that we know that the representative disk will not map perfectly the old star formation. Also, this is because we have the gradient in age. So for a simulation that does not have gradient in age in the center part, this would be perfect and would follow the ideal case. But we do expect the gradient in age. So this is to show that, yes, we do expect that our methodology works. Maybe they timed the bar formation a little bit before, but we still can find the epoch of the bar formation. So how does this look for galaxies? Our pilot study is NGC 1433. And this is how it looks for this galaxy. So we have now the original data, we have the representative main disk, and we have the subtracted disk in blue now. And for this case, we have a bar of 10.5 gigayears, which makes sense with a lot of characteristics of this galaxy's bar. So this bar has all the characteristics you could expect from an old bar. That is a flat profile, you have a bar to total ratio that is big, and so on and so on. So all of this makes sense with observed properties of this bar. Of course, we were also wondering if for a galaxy that does not have a nuclear disk, what does happen with this methodology? Do we artificially produce this kind of result or not? So we also have a control galaxy, NGC 1380. And now I am showing you both galaxies to make clear that if you don't have a nuclear disk, you will not have the ratio above 1, and you will not have artificial ages for bars that does not exist. So this is to show you that this is a reliable methodology by simulations and also by control galaxy. So we went further, and we also wanted to investigate the inside-out growth of the nuclear disk, if this scenario that was recently proposed made sense or not. So now what we have here, what I'm showing you, is the star formation history for different radii. So purple is inside and yellow is outwards, okay? So, and in the top, you have the mean age for different star formation histories. We can see that from purple to yellow, the mean ages, they do get younger, but it's not that evident. So if we do the same exercise for the subtracted data, the isolated nuclear disk, this becomes way more clear. And in fact, this is consistent with the inside-out growth of nuclear disks, at least for this galaxy, NGC 1433. The second consequence for the inside-out growth, we could expect that smaller nuclear disks will have younger bars. So we also apply the same methodology for three very small nuclear disks. As far as we know, they are among the smallest nuclear disk that was observed. And these are these three. So the smallest ones, they have 75 parsec, which is very, very close of the simulated radii of the smaller expected nuclear disk. And we can see that they are younger. So if for NGC 1433, we had a bar of 10 gigayears, and now all the ages are around 4 gigayears for smaller nuclear disks. This starts painting a picture of the relation between bar age and nuclear disk size. Of course, we still don't have enough data. We only have some examples, but this starts looking like you can differentiate between old bars and young bars using this methodology. And maybe you have a relation with the nuclear disk size, which is still not clear. In the future perspectives of our work, we want to apply the same methodology for the whole timer sample, and we have plus 20 galaxies to see how this picture actually looks like for a larger sample. So just some takeaway messages to summarize what I presented here. Well, first is a new methodology to separate the nuclear structure. So subtracted data cube, nuclear disk, and the representative main disk that will be below the nuclear disk. Second, we use the star formation history to time the moment that the bar formed, and we consider the ratio between subtracted over representative. The moment that this is above 1 is the moment that the bar forms for the first time. Third, for NGC 1433, when we analyze star formation histories for different radii, it does look like this galaxy has an inside-out growth, meaning that the outer part of the nuclear disk are younger. And lastly, we do expect that smaller nuclear disks have younger parts. It's still a bit soon to paint this picture, but with time and applying this to a larger sample, the timer sample, we expect to be able to draw this picture a little bit better in the very recent future work. So thank you so much for watching this talk. If you have any questions, feel free to contact me through Slack. And as I said, we are looking forward to submit this very soon and have this out there. Any questions, just please contact us. Thank you.